We are starting chapter 4, section 4.1, and this video is, I predict, going to be longer than most of the other videos because we are going to introduce the basics of graphing our sine and cosine functions. We're going to be graphing with transformations like you did in college algebra, so it should be familiar to you, but there's just a lot of moving parts, kind of, sort of, so this is just going to take a few pages to get everything down so that you have some good examples and some good foundations. Now, in this section, we're focusing on just graphing these two functions, sine and cosine. You've probably seen a sine wave graph before. If you haven't done so, I want you to stop and watch it's like a 30-second YouTube video that I posted in Canvas that talks about how that graph of the sine wave is rolled off of the unit circle. It's a really good visual example of what we're doing. Sine and cosine are just a horizontal shift apart. But let's start with some definitions. Okay, our trig functions are what we call periodic functions. A periodic function is just a function that repeats in a regular pattern. A function that repeats in a regular pattern. The period is one complete pattern. For example, for our sine or cosine that comes in a wave pattern, we count one period as peak to peak, so from the top of the wave to the top of the next wave, or trough to trough, so from the low point of the wave to the low point of the next wave. We also talk about a period as being a cycle. The amplitude is the height, but it's the height from the center to the peak or to the trough. It's that difference, though, from center. Examples of other types of periodic functions would be your heartbeat. If you have a normal heartbeat pattern, that's going to repeat in a nice periodic function. Okay, now we have a more mathematical definition. Periodic functions such that this f of x is going to repeat for every period, every real number x in the domain, every integer n, some positive number p. That least possible positive value of p is going to be the period of the function. So it's going to repeat. It happens, and then it's going to repeat every period, every time it comes back around. That's the easiest way I can put that in. The circumference of my unit circle, the distance around my unit circle, is 2 pi. So that least value of p for which sine and cosine function repeats is that one rotation, or 2 pi radians. Therefore, we say that sine and cosine are periodic functions with a period of 2 pi, and the following statements are true for every integer n. So sine is going to be a periodic function repeated every 2 pi radians. So one rotation of 2 pi, 2 rotations of 2 pi, 3 rotations of 2 pi, etc., etc. And then the same is true for cosine. They are both periodic over 2 pi radians. Now, on my unit circle, because that video talks about rolling that sine function out from the unit circle. The unit circle is my jumping off point. It's my standard set of values before I do any transformations, before I change anything away from the parent function. Remember, on my unit circle, sine is my y value, cosine is my x value. So I have been shifting papers here. Let me see if I can find, there it is, there's my unit circle. So as I rotate through my unit circle, what is happening? From 0 to pi half, so for my first quadrant, my sine function value goes from 0, it's increasing all the way to 1. And my cosine function value is starting at 1 and decreasing to 0. Let's focus on sine function all the way around to start. So we're going to look at our y values first. So through the first quadrant, my sine function value is increasing from 0 to 1. And then in the second quadrant, from pi half to pi, my sine function value is at 1. It starts decreasing back down to 0. So it decreases from 1 to 0. When I move into the third quadrant, from pi to 3 pi halves, my sine function value is at 0 here at pi. It starts decreasing, so we're moving in a negative direction to a -1. Decreases from 0 to -1. Once it gets down to -1, that is the least value of sine, it starts increasing back to 0. So my sine function cycles through from 0 up to 1, back to 0, down to -1, back to 0. What about cosine? Well, when I start in my first quadrant, now we're looking at the x-coordinates, cosine is at 1, and this is the largest value for the range of my cosine function. Cosine goes from 1, it decreases to 0, and then in quadrant 2 it continues to decrease to a -1. So from 0 to pi, cosine is decreasing from 1 to 0 to -1. Let's fill those two in. From 0 to pi half, cosine decreases from 1 to 0. When I get to pi half, from pi half to pi, it continues decreasing from 0 to -1. Now I'm over here at pi. Cosine, my x-coordinate, is -1, and it starts increasing again. It starts moving back to 0. My x-coordinate is moving back to 0 from -1 to 0, and then it continues increasing all the way back to +1 when I'm over here at 2 pi. So from pi to 3 pi halves, I go from -1 back to 0, and then from 3 pi halves, that quadrant 4, I go from 0 all the way back to +1. So my sine function value is waving through. Sine function at 0. When I start with an angle of 0, it goes up to 1, back to 0, down to -1, back to 0. That is one cycle of sine function. Cosine function, where my angle is 0, cosine function starts at 1. It cycles through 0, down to -1, back to 0, and then back up to +1. That's my cosine function. We're going to see if we continue and do more than one cycle that this pattern repeats. It's the same pattern. It's just that I've shifted it so that my cosine is starting at that peak instead of starting at center. Alright, let's look at our next page of notes. I know it's a lot. Bear with me. Keep remembering that we're going to see lots of examples and that you can always pause and repeat this video, which makes it really nice. So for my sine function graph, f of x equals sine of x, where x is my angle theta. That's my domain of my function. And f of x is the output. It's the value of the function, which is my range. So when I'm graphing sine, I can use any function, I can use any angle. I can plug in any angle into my domain. So my domain is all real numbers. Any angle works. When I get out my sine functions, we just cycled through the range of sine function values. The lowest value was -1 and the biggest value was +1. So my range is from -1 to 1 increasing, and we've looked at that before. Now this we're just filling in from our unit circle. Where x is 0, our sine function is 0. Where x was 1/2, sine function is 1. Where x is pi, our angle is pi, sine was back to 0. At 3 pi halves, my sine value was -1, and at 2 pi, I had cycled back around to 0. Now, it also included the other special angles in quadrant 1. Sine in quadrant 1 goes from 0 to 1/2 to square root 2 over 2 to square root 3 over 2 before it hits its maximum at 1. Notice it skips all those other special angles and just does the quadrantals for the rest of the circle. These quadrantal angle values, those 5 function values, 0, 1, 0, -1, 0, center, peak, center, trough, center. Those 5 function values gives me 1 cycle of sine function, or 1 period, which means that right here I have one other cycle or one other period. Cycle and period are used interchangeably because I have center, peak, center, trough, center. Those 5 function values define a cycle or a period of my sine function. Sine is continuous over its entire domain. Its domain is all real numbers. I can plug in any angle. Its x-intercepts, center, are in the form of n pi because that is where my sine function value is 0 at those full values of pi. -2 pi, -pi, 0 pi, 2 pi, 10 pi, -15 pi, that's where I'm going to hit center. Now keep in mind that this is my parent function. Just like in college algebra you would have families of functions, this is my parent function before I start messing around with it. This is the most basic form of the sine function. Period of sine is 2 pi. It hits all of those major values in one rotation, or 2 pi radians. This graph is symmetric with respect to the origin. It's an odd function. Hopefully you remember that from college algebra as well. When you look at the graph of an odd function, it's got that twist in the middle. It's balanced on the origin. One side's up, the other side is down. What that means for us algebraically is that when I plug in a negative x, I get out the opposite of what I started with. Symmetric with respect to the origin. So for example, the sine at pi half is 1. The sine at negative pi half is -1. This means, what this last statement, that it's an odd function, also means that if the point xy belongs to the function, then so does the point -x, -y. If I plug in a negative x, I get out a -y, the opposite of y. So the sine function value at pi half is 1, and the sine function value at negative pi half is going to be -1. Domain and range, domain and range. Angle and sine function, angle and sine function. All right. So once again, putting it down in words so that you can remember, the parent function is built from the unit circle. That is our jumping off point before any changes are made. Once we change something, the amplitude, the period, etc., we can no longer go back straight to the unit circle because the values have changed. Even though the function is still moving in the same way, the same shape is the general shape is the same. It is not going to be able to be graphed right back where it was. For example, from college algebra, everyone hopefully remembers your parent function for the quadratic equation, f of x equals x squared. That's what that's going to look like. Well, if I do some stuff to that, let's say I've got g of x is a -3 x minus 2 squared plus 5. I've got transformations of functions going on. I still have a parabola, but what have I done to that parabola? Well, I've moved the vertex from the origin. Now my vertex is going to be at 2, 5. Over 2, up 5, there's my vertex. I've stretched it by a factor of 3. I made it skinnier and I flipped it upside down. That's what that negative out in front means. So it's still a parabola, but it's a long, skinny, upside down parabola with a vertex up here instead of at the origin. Now, this pattern of transformations that I just walked you through super fast and you went, oh, wait, I don't remember. It's okay. I'm going to walk you through the pattern of transformations specifically with trig functions here in a minute. But first we're going to look at our cosine function graph so that we can compare it more directly to our sine function. So grab your next page of notes. Notice that as you grab this next page of notes, the graphs they built for you for sine and for cosine look almost identical. Focus on where it hits on the y-axis. Where's my y-intercept? Okay. So let's focus on cosine. We're going to walk our way through our parent cosine function. And then we are going to look at that pattern of transformations. All right, the graph of the cosine function is in fact the graph of the sine function shifted or translated pi half units to the left. Now this is my parent cosine function graph. F of x equals cosine of x. I am still plugging in an angle and getting out a function value. My angle can be anything. My domain is all real numbers. I don't have any restrictions. The range, however, think about those cosine values, those x values that we found on our unit circle. My range is always going to be between -1 and 1, inclusive for both sine and cosine. Now let's walk through these values from our unit circle. Cosine, at my angle 0 radians, cosine is 1. Let's look at our quadrantals first. Cosine is 1 when I'm at 0 radians. Pi half, I'm at 0. At pi, cosine is -1. So x value goes from 1 to 0 to -1. At 3 pi halves, my x value is 0 again, and back at 2 pi, my x value has gone back up to 1. Those are my quadrantal angles. That's my 5 points that are going to show up to make one cycle or period of my cosine function. The other values are those special angles in quadrant 1 that show you how it's moving incrementally. My x-coordinate at pi 6 is square root 3 over 2. Then I go to square root 2 over 2, and then I'm at 1/2 before I hit 0 at pi half. These are my x-coordinates, those cosine function values that come out when I look at the angle as my input. So my 5 major points. Cosine starts at peak, cycles through center, trough, center, back to peak. That is, those 5 points give us one period or one cycle of cosine. I can keep going in either direction. Anytime I identify those 5 points, I have one period or one cycle of my cosine function. Now, cosine is continuous, it's infinite, my domain is infinite, so it just keeps moving in that wave forever to positive infinity and negative infinity. Okay, so what do we know about cosine function? The cosine function graph is continuous over its domain, all real numbers. I can plug in any angle for my domain. The x-intercepts, it hits the x-axis at the pi half, odd pi half values. Sine function hit it at the full pi values. Cosine hits it at the odd pi half values, at k pi halves, where k is an odd integer. Where k is an odd integer. I couldn't get this this part of the notes to switch for me. Where k is an odd integer. Cosine is also periodic over 2 pi, just like sine. Cosine is symmetric with respect to the y-axis, so it's an even function, which means when I plug in a negative x, it doesn't change anything. I still have the original function value. So the fact that it is an even function, it means that if xy is in the function, it's a point on the graph of the function, then so is negative x, y. So x changes to negative x, y stays the same. So, for example, at 2 pi, my cosine function value is 1. And at negative 2 pi, my cosine function value is 1. So 2 pi or negative 2 pi, my cosine function value is 1. Positive pi half or negative pi half, my cosine function value is 0. All right, even function. Cosine is even. Sine is odd, cosine is even. Now, here's what I promised you, that pattern of transformations of functions. You learned this in college algebra. The same pattern of transformations holds true for your trig functions. Your variables are probably going to be a little bit different than what you learned in college algebra, but that's okay. We're going to identify them now. Now, it says cosine. It could be sine, secant, cosecant, tangent, cotangent. Does not matter. It's just a trig function. When I put a coefficient in front, that is my stretch or shrink, my vertical stretch or shrink. It represents, for most of these functions, what we're going to call the amplitude. How high is the peak? How low is the trough from center? So in my parent sine and cosine function, my amplitude is 1. I don't have a coefficient other than 1 in front of my function value. It's just 1 cosine x or 1 sine x, so it goes up to 1, down to 1. 1 unit from center. A is for amplitude here. B, now notice that I got some stuff going on. I got some grouping going on here. So B is a coefficient on the x, but we assume it's been factored out. So B is going to be my period change. We can also call that a horizontal stretch or shrink, where my amplitude was a vertical stretch or shrink. C is my vertical shift. So I will move center away from the x-axis if I have a value for C. C is usually out in front with my trig functions. In college algebra, we would see added or subtracted on at the end. And then finally, D is my horizontal shift. We're going to call it a phase shift. We take our graph and we shift it to the left or the right. Notice that just like in college algebra, it starts out as x minus. So if this is a positive pi half, I've shifted it to the right. If it's x minus pi half, I've shifted it to the right pi half units. If it's x plus pi half, that means I had to have plugged in a negative pi half here, and I will have shifted it to the left. My period is defined. We have a period change here. My period for sine and cosine starts at 2 pi. So if I adjust that period, I do 2 pi divided by b, whatever that value for b would be. I take my original period of 2 pi on my parent function and I divide it by this coefficient b that causes me to have a horizontal stretch or shrink. It compresses the wave or it elongates that wave and stretches it out. Alright, I warned you that this was going to be a longish section. Here we go, third page. Right, third page, fourth page. Fourth page, that's good. But we're just now getting started on our graphs. So I am already seeing that we are going to split this section into 2 different videos. We'll get through a couple of examples at least, and then we'll take a break and we will split the video to a new video and we will pick up in another video. Okay, let's start out with some basic sine function graphs. We're going to graph y equals a sine of x. Remember that a is my amplitude. It's a vertical stretch or shrink. a vertical stretch or shrink. It affects my amplitude. And we're going to compare it to the graph of y equals sine of x. So let's start by graphing y equals sine x. Let's just start there. Y equals sine x is our parent function. So our amplitude is 1, our trough is -1. It's periodic over 2 pi. So I'm going to take my 2 pi, that period, I'm going to divide it into 4 equal intervals. If I cut it in half, that would be pi, and then I cut that in half, and that's pi half, 1 pi half, 2 pi halves, 3 pi halves, 4 pi halves, and I've divided my period into 4 equal intervals. My parent function, sine function, starts at 0, goes to peak, center, trough, and back to center. That's 1 period, 1 cycle of my parent sine function. Let's set it up. We are not going to set up coordinate charts except for right this second. Typically we do not do this. So I'm plugging in angles, and my angles I'm going to plug in are 1 period, my quadrantal angles. So my quadrantal angles for 1 period, 0, pi half, pi, 3 pi halves, and 2 pi. 1, 2, 3, 4, 5. Those are the 5 quadrantal angles we're going to be looking at. Now, my first function is my parent function, y equals sine x. If you need to reference your unit circle, at 0 radians, my sine function value is 0. Up at pi half, my sine value is 1. Over at pi, my sine value is back to 0. At 3 pi halves, my sine function value is -1, and then when I come back around to 2 pi, I've done a full cycle and I'm back to 0. So there's my coordinates. 0, 0, 0, 1, pi 0, 3 pi halves -1, and 2 pi 0. There are my 5 major points that we graphed for 1 cycle of y equals sine x. Now what we were asked to look at was y equals 1/2 sine x. So let's do that. Now we already know sine of x, so we're just going to multiply this coefficient 1/2 by that function value. So at 0 radians, sine of 0 is 0, 1/2 of 0 is still 0. At pi half, sine at pi half is 1. 1/2 times 1 is 1/2. Half of 0 is 0. Half of -1 is -1/2, and half of 0 is 0. So when I come over here to graph y equals 1/2 sine x, notice the color coding. I'm just going up halfway, back to 0, down halfway, back to 0. So the cycle is still the same. The period looks the same, except that my amplitude has changed. My amplitude here is 1/2. So for my parent sine function, y equals sine x, my range was from -1 to 1. For my transformed sine function with an amplitude of 1/2, my range is now from -1/2 to +1/2. That change in amplitude changed the range for my sine function. Let's do it again. Y equals 2 sine x. We're going to start with 1 period. You know what? Let's do 2. Let's go from -2 pi to 0, there's 1 period, and then 0 to 2 pi, there's another period. We're going to start with y equals sine x. Divide each period, there's 1 period, in 1, 2, 3, 4 equal intervals. Here's my other period divided into 4 equal intervals, and I'm going to label those. The things that you see me doing here are the things that I will expect you to do on written assignments, so make sure that you're paying attention to that. So my range for my parent sine function is from 1 to 1, 1 to -1, excuse me, 1 to -1. Parent function starts at 0, goes to peak, center, trough, center. When I cycle through back the other direction, it follows the same pattern. It's just curving back. We could do 4 cycles or 10 cycles if I asked you to. I won't ever ask you to do 10 cycles, but I might ask you to do 2. So there's 2 cycles of my parent sine function, 2 periods. What about this transformed sine function? Well, for my transformed sine function, a is 2, so my amplitude is 2. This is a vertical stretch. That means from center, it's going to go down 2, and from center, it's going to go up 2. Center is 0. So I need to go all the way up to 2 and all the way down to -2. It's going to hit the same center. It's just that my peak and my trough have been stretched. So when I have that whole number for my amplitude, that whole number that is greater than 1, it's just stretched out that amplitude. So it follows the same cycle as my parent function, it's just stretched out. Now notice when I had a fraction, proper fraction, I had a compression or a vertical shrink. When I had a whole number, I had a vertical stretch. We can think of the graph y equals a sine x as a vertical stretching when that absolute value of a, don't worry about if it's positive or negative, when it is greater than 1, so it's a whole number. And we can think of it as a vertical shrinking when that absolute value of a is less than 1, so it's a fraction. It's going to make the amplitude smaller, and it's a shrink. This states it algebraically or mathematically, puts it in better mathematical language for you, but that is saying the same thing that we just said. All right. Now, I'm trying to decide, that's 30 minutes. You know what? I'm going to cut this video. We're going to make a part B for section 4.1, and we are going to pick up with example 2 when we come back to the second video, part B.